All right, this is going to focus on interpreting a thermochemical equation. So you all know what a chemical equation is. Thermochemical just means we're adding heat to it. So you're going to see that that includes reactants, products, and heat. So there's two methods to do that. So typically you'll see a positive delta H sign to show that a reaction is endothermic. So you'll see I have an example of that here. And a negative delta H shows that it's exothermic. So you'll see that these are the same equations, just in reverse. Okay. So we can do this with the values with the delta H, or the numbers can be embedded into the equation. So sometimes you will see it embedded here. So if it's endothermic, heat will be a reactant. If it's exothermic, heat will be a product. So just be careful. Notice that this plus sign is used because it's part of the equation. So it's, again, a product. Don't confuse that with the delta H value that is positive, which is using the delta H value to indicate what type of reaction it is. So that can be confusing. So just look at the style. If you see delta H, the sign here is going to tell you exothermic or endothermic. And if it's embedded in the equation, this is going to tell you endothermic and exothermic based on which side of the equation it's in. So just be careful with those notations. If you don't see a plus sign and you just see a value out here, then we're back to these types of notations. Okay. All right. So you can calculate the heat of reaction from the delta H of reaction. So heat is extensive. So just like mass volume, it's proportional to the amount of substance reacting. So if you have more stuff, so the best example I can give you that is burning wood. If I have a toothpick, I don't get as much heat out of a toothpick as I do burning an entire log. So that's that size relationship. So you'll see I have the equation from above, formation of water from its elements, and its heat of reaction is negative 484 kilojoules. Oftentimes you're going to see these in terms of 1 mole of substance. So again, we don't balance a lot with fractions, but you do see this quite a bit in heat problems. So what they did then is divided all of this by 2, okay, in order to get from 2H2 to 1. You'll see 1 divided by 2. So again, I'm just dividing each of these, so this is a 1, to get the numbers that are here. So 1, 1/2, and again 1. And once I do that to the heat values, I have to also divide this by 2, and I'm going to get negative 242 kilojoules, or 1/2 of the negative 484. So the sign doesn't change, just the magnitude. So sometimes you'll see these as just kilojoules, but they really are in terms of moles, since equations are balanced in terms of moles. So our next little problem here, we have the thermochemical equation for aluminum oxide, and the normal way we would balance this is 4 aluminums plus 3 oxygens yields 2 aluminum oxides with the heat of reaction of negative 3,352 kilojoules. So if we want this for 1 mole, we've got to get this to 1. So I'm going to divide this by 2, and whatever I do to one part of the equation, I have to do it to all of it. So I'm going to divide 4 divided by 2, and that's going to give me 2 LAs. I'm going to get 3/2 O2. I know that's going to look strange to you, but 3 divided by 2. And then 1 mole of aluminum oxide. And again, whether you bring the phase notations down or not, I'm not too worried about that for this, but there are problems in heat that phase notations do matter. Okay, and then I need to do the same thing with my heat. I have to divide this by 2, and that is going to give me a delta H of reaction as negative 1676 kilojoules. Okay. All right, on the back, we're using that same equation. So when aluminum metal is exposed to atmospheric oxygen, as in aluminum doors and windows, so any place the aluminum is exposed, it is oxidized to aluminum oxide. So that's the equation we just did. How much heat is released by the complete oxidation of 24.2 grams of aluminum at 25 degrees Celsius and 1 atm. So It didn't specify that, but this is sort of the standard conditions for measuring heat. So just like gases, the standard temperature is 0. Heat, the standard temperature tends to be 25 degrees. So I'm going to start with the equation that's given. So if you have the option with problems, you want to make sure that you use the given information. So if you would have made a calculation in part A, that error would show up in part B, but since we have the original, I'm going to use that. So I'm just copying what I had from the front page. So, so this original given equation is what I'm using. Okay. So I have 24.2 grams of aluminum, and I want to know how much heat. So the aluminum is my given information, and I want heat, so that is going to be in kilojoules. Okay. So it's aluminum, so I'm going to go to the periodic table and get aluminum is 26.98 grams per mole to cancel my grams. And then I'm going to treat this as any other type of stoichiometry. For every 4 moles of aluminum, okay, that's how I'm going to get rid of my aluminum there, and my moles, I'm going to get this negative 3,352 kilojoules. Okay. And when you calculate that out, you should get negative 752. Now, it shouldn't matter if you use the equation that we just adjusted. You'll see that you get exactly the same answer. So the molar mass doesn't change, but what happens here is you're going to have the negative 1676 kilojoules for every 2 moles of aluminum. But again, when you calculate that out, you should get exactly the same number. Okay. All right, so a couple little questions with this. Just be careful, units can be kilojoules or kilojoules per mole. Look at the context of the problem to determine if 1 mole is implied, or the kilojoules relates to the specific equation given. So again, if they just give you a heat value for a substance, then that's based on 1 mole. But if they give it to you for an equation, so if we go back to our original examples here, this is for the specific ratios. So just be careful. If they give you this, it's going to relate to the equation. If they give you the, there's actually something called heat of formation for water, you're going to see that that's half of that value because it's based on 1 mole. So you're just going to have to kind of do some practice problems and get used to looking for that. The physical states of species are important, and they really should be specified. That's going to come up in the next chapter or next section of this chapter, where phase notations are very important. And again, delta H is usually measured at 25 degrees, but it doesn't change significantly with moderate changes in temperature. So again, if we're working around room temperature values, they're going to be consistent. Now, if you're doing an industrial process where it's high heat or very cold temperatures, then there may be a factor. And you're going to use your same stoichiometric and mole relationships if you're given masses, moles, volumes, and or molarity. So don't forget what you already know about converting units. It works the same here, just like we did up here with our molar mass of aluminum. Okay, and there is a problem set to go with this. This is also in the assignment section of Blend. Okay, so check Blend for the due date.